Hi, and welcome to the Ground Source Heat Pump Association Training Academy. My name is Chris Davidson. This is the second of three training sessions for training standards officers, and the aim of these sessions is to give you some tools to understand heat pumps and spot the problems that might come along. Today we're going to go into a bit more technical detail and give you an overview of how heat pumps work. We'll then describe the different sources of heat available and the solutions that we can use to access them, and introduce you to how efficiency is measured, installed costs and resulting savings, so if you can see what is a credible installation. So first of all, what are heat pumps? A very simple way of putting it is that heat pumps are boxes which move heat from a cold place to a hotter place. And you almost certainly own several heat pumps. Fridges, freezers, air conditioning units in cars, and even some tumble dryers are all examples of heat pumps that we've had in our homes for many years. The move now is to use those heat pumps and use that technology of heat pumps to heat and cool buildings. So how do heat pumps work? I'm going to take you back to school, and I'm sure an experiment that you all did, which is boiling some water. So we're applying a fixed source of heat, a Bunsen burner, to a beaker of water, and we're measuring the temperature as we go along. What you'll find is that the temperature increases as a straight line, so it's a steady linear increase in temperature until we reach boiling point, which is when the water is turning from a liquid into a gas. And if you continue to plot the temperature, what you'll find is that whilst the heat is still going into the beaker of water, the temperature is now not increasing. So the energy is going in, but that energy is now being used to pull the molecules apart from each other and turn the liquid into a gas. The energy is still being absorbed though, and that's the important point in a heat pump. The energy is being used to change the state of the matter. If we carry on heating, and don't try this at home, by putting a lid on it, then you would actually find that the temperature rise would carry on and the pressure would increase. Quite a dangerous thing to do, hence the safety mechanisms on a pressure cooker. There is one other bit of physics we need to understand to describe how a heat pump works, and that's as the pressure increases, the boiling point increases, and as the pressure decreases, the boiling point also decreases. And so if we design a heat pump to manipulate that pressure, then we can manipulate the point at which the water or gas changes phase from liquid to gas and vice versa. And that's what a heat pump does. We manipulate the pressure in the fluid to control the point at which it boils and condenses. And bear in mind, as it goes through that phase change, the energy is still being picked up, or is picked up by the fluid or dropped by the fluid. So when it boils, we pick up the heat in the evaporator, and when it condenses, we drop it again in the condenser. So we pick up heat at a cold, low pressure regime and drop it at a high pressure, high temperature regime. The thermal expansion valve, which is the little cross at the bottom there, that's really just a pinhole which keeps the high pressure on one side, and that high pressure is created by the compressor. The compressor itself consumes electricity, so it's not free energy. The laws of physics wouldn't allow, but so there is electrical consumption that's required to run the heat pump. So let's talk about some heat pump types and the sources that they employ. So first of all, we've got air source heat pumps. They have got fans in them. They are situated external to the building, so they've got to be in contact with the air. The fans draw air through, and the heat pump sucks heat out of that air and delivers it into the building. We also have ground source heat pumps, and these source their energy from the ground. So they can use boreholes, they can use horizontal trenches, they can use water wells, they can use ponds and lakes, and they can even use mines as a source for their heat. We can also hybridise, so we can have a heat pump, either a ground or an air source heat pump with conventional technology. We might have an air source heat pump and a ground source heat pump, lots of different combinations of technologies to get the heat into the building. One word on hybrids, however: the more technologies you employ to heat and cool a building, the more complex the system becomes, therefore the more difficult it is to design and install. Let's talk a little bit more detail about ground source, because rather than just being a box which sits outside, ground source is best thought of as a system. So a system of a heat pump and a source. So these vertical boreholes will tend to be 150 millimetres in diameter, thereabouts. They are drilled to between 100 and 300 metres deep, sometimes deeper, sometimes shallower. Most of the time, each borehole contains a single U-tube of plastic pipe, which you can see here, and that pipe is grouted into place using a cementatious grout material, which is pumped into the hole. It's obviously very important to get the correct amount of pipe in the ground to sustain the heat loads that are required for the building, and that's critical as part of the design of the system, be it vertical boreholes or the other types of system we're now going to talk about. We also have the opportunity to utilise horizontal trenches. Now these trenches will typically be a metre wide and somewhere between 1 and 1.5 metres deep, and they'll contain various different designs of pipe. In the picture there you can see straight pipes. You might also have seen slinkies with coils of pipe inside those trenches. The design of it is slightly different, and the geometry really that's utilised is up to the designer and the installation methods being utilised. So we may have available to us narrower bucket digging machines or wider, and the design needs to be reflective of that. We can also use water wells. Less common at the domestic scale, although it absolutely can be done and is done at the domestic scale. And water wells are holes drilled in the ground which we can pump water from. They are much bigger in construction terms than closed loop vertical boreholes, and they often require licensing. So any time that the consumption is over 20 metres cubed a day, a statutory licence would be required in England and Wales. The rules are slightly different in Scotland, whereas SEPA can actually allow licences provided all the water is taken from the ground is put back in. So quite a complex field. It is a different installation process from closed loop, much bigger in construction terms. Ponds and lakes are incredibly effective sources of geothermal ground energy. So we can very simply put coils of pipe or steel plates into a pond or lake, and we can deliver huge amounts of energy very, very effectively and very efficiently from that. What's important is to size the system such that, and size the lake such that it's not going to run out of energy. So we're not taking more out than is being replenished by the sun, and we're not, if we're cooling, putting too much heat back in so that the lake would ultimately evaporate. Finally, mines are a solution. Very unlikely that this would be a solution for an individual domestic system, but certainly multiple domestic systems. And you can see in the map there, the shaded areas surrounded by black are the areas that are undermined in the UK, principally with coal mines. And you can see it's a remarkably large amount of the UK is undermined, and these represent a significant resource for geothermal energy, both now and in the future. So let's now deal with how we define efficiency of a heat pump system. And it's defined by a term called coefficient of performance, COP. And what I like to think of is, what is a customer going to be interested in? Well, I'm interested in how much heat is delivered into my property and how much electrical energy is being consumed to do that. And if we divide that heat delivered by the electricity in, then we get coefficient of performance. And it could be a number between 1, which is 1 unit of electricity in and 1 unit of heat out. So that would be, for example, a direct electric heater. Right the way up to 4, 5 and 6 units of heat delivered for every unit of electricity consumed. I'm going to talk about typical numbers in ranges in just a second. Be aware of the difference, however, between a rating point coefficient of performance and a seasonal coefficient of performance. A rating point COP is simply at a given temperature point, that heat pump will deliver that amount of heat for that amount of electrical consumption. It will change. So as the difference in temperature between the source of heat and the load increases, the efficiency of the system will decrease, i.e. the electrical consumption will increase. So think about it like if I'm climbing a small hill, then I don't need as much energy as if I'm climbing a big mountain. And that is a good way of thinking of COP. So at a given point, the COP might be a number. But to really understand how the annual performance of that system is going to fare, and directly how the electrical consumption is going to vary, you need a seasonal COP, which varies with the temperature of the source primarily. So as the air temperature changes for an air source heat pump, that COP will vary throughout the year. As the ground loop temperature varies, as we get towards the end of the heating season, it will get colder. Then again, that COP will vary. And to understand it throughout the year, we need to measure it and model it accurately. And the important point is that really the seasonal COP is the only true measure of performance on a system. So comparing rating points of products, which is very commonly done in the sales environment, is not an ideal way of comparing products and systems. Again, efficiency is directly proportional to the temperature difference between the source and the load. And the point I would make there that's critical is if that source is not designed properly, particularly in the case of ground source, it can get colder, therefore less efficient. And if the heat emitters are not considered properly, particularly in a retrofit environment, if a proper assessment of the heat emitters is not made, then you can sacrifice performance very, very easily and quickly. So how do we measure that efficiency? Well, the seasonal COP of an installed system can be measured by measuring the electrical consumption with an electrical meter on the heat pump and the heat delivered using a heat meter, for example. And that will give us, if we go over a whole full year, the seasonal COP by dividing that heat into the dwelling divided by the electrical consumption. But actually accurately measuring heat, particularly on a heat pump system, is quite challenging because for heat pumps, as opposed to boilers, the flow rates are relatively high, the water flow rates are relatively high, and the temperatures in and out, the difference between those two, the delta T as we call it, is relatively small. So small errors in either flow rate measurement or temperature measurement can have quite a big effect on how accurately you're measuring the heat. So the good news is that under the microgeneration certification regulations, the MCS, which I'll talk about next time in a bit more detail, electrical metering is required and it actually can diagnose almost all problems. So if you're seeing electrical consumption that's out of kilter with either the heat pump performance or the consumption or the heat that's being delivered into the building, then you've got a problem. That problem could be the building is requiring more heat than it was designed to, or it could be that something else is wrong with the system. The ground loop might be too small, for example, so it's getting colder than is needed. The heat pump might be faulty. So that electrical metering is really valuable in any heat pump installation. So what about real world efficiency then? What numbers can we anticipate to see? Remember that rating points, and I'm emphasising this, rating points are a very poor way of assessing efficiency. So looking at the brochure and saying at 0 degrees water temperature in the source and 35 degrees water temperature on the load, that is going to give you a very narrow view on the efficiency of a product. So remember that always. And actually, what you'll tend to find, because the rating points between air and ground source are different, you'll tend to get an overstatement of seasonal COP or an over impression of seasonal COP if you look at air source. If you look at ground source, the opposite is true. The opposite is often true because of the points the rating points are at. The other point on air source is that when the weather is cold, not too cold, and the air is damp, then there'll be frost forming on the coils of the air source, and that needs to be defrosted or the air can't get through. So that will have an effect on efficiencies also. And as I said, ground source tends to perform better over a seasonal basis than the rating points would suggest. So to give you a number, typical UK seasonal performance for air source would be about 2.2, so it's delivering 2.2 kilowatts of heat for every kilowatt hour of electricity consumed, and ground source would be 4. There's a plus and minus on that. I would say you've got at least 25% plus or minus on that, maybe even 50% plus or minus. If you were at 50% lower than this, then you would say a system would be poorly designed, or at least would need further investigation. If you're 50% better than that, great, you've got a really good installation. But that's a middling ground type number for both air source and ground source. So now I'm going to give you some numbers on installation and run costs. Now these again are very rough numbers to give you an idea if a system is in the right ballpark, if it's being missold or not. So there are several factors that influence cost. Size of the project is a huge factor in cost, particularly for ground source. So if we've got 20 houses to install, then the cost per dwelling will be completely different, much lower than if you're doing one dwelling. Similarly, if you're doing 200, again, it will be lower again, because the economies of scale kick in, as I say, particularly for ground source. The source involved, again, has a huge effect on the run costs. And I'm going to go through a comparison of the different sources in a second in terms of the effect it will have on the cost. The complexity of a project will vary. Now, why would the complexity vary? For example, as I mentioned earlier, a hybrid between a heat pump and a conventional technology would add complexity to the system. Whether it's new build or retrofit, again, makes a difference. In a new build system, you can purpose design the emitters to suit the heat pumps much more readily than perhaps if you've got a retrofit system, where you've got what you've got in terms of distribution. Yes, you can make upgrades and changes to it, but that's much more expensive. And then finally, client requirements. Very often the client requirements will drive a system cost up or down. Very often, if you're doing, for example, multiple social housing retrofit, then the client requirement is for an economic installation. Whereas you might be looking at a big house where a real showcase system is what the client is after. So that will drive the cost of the installation. And as a very rough guide, and really only a guide, air source, you're looking at, for a complete installation, somewhere between £6,000 and £12,000. For a ground source, you're looking at something from 9 to 24,000. Obviously, if you go bigger in systems, so this would be a domestic scale. If you go bigger in systems into commercial buildings, then you could be into hundreds of thousands or even millions of pounds for these installations. But that's a rough guide for a domestic system. On the run cost side, calculated run cost is actually pretty straightforward once you've got the seasonal COP. And again, it must be the seasonal COP, not that rating point COP that you're using to calculate, either estimate or calculate post-installation the run costs. Of course, you also need to understand the fuel costs, and that can have a big bearing on the run costs of the system. So once you've got your fuel price and your COP, you're simply dividing the heat being delivered into the building by that COP, which gives you your electrical consumption, and multiplying it by your fuel price, your electrical fuel price. So very simple to calculate what the run cost ought to be for that system, particularly against manufacturers' claims and installers' claims of coefficient of performance. So it's relatively straightforward to do the arithmetic on that. To give you some numbers again to conjure with, and again, very rough numbers, an air source in a retrofit will cost something like £1,950 a year to run. For a new build, something like £800 a year. And again, a ground source retrofit, just over £1,000 a year, and a new build, something like £400 a year. Very much depends on the size of the property, and again, this is for a typical domestic installation. Very dependent on fuel costs, as I say, and very, very much a guide. So let me just give you a summary of the heat pump economics by source type. Let's compare it to a direct electric system. So underfloor direct electric becoming more common, storage radiators, that kind of thing. Installation cost is very, very low. Hence, it is very attractive to developers who have got an eye on that low initial cost of the system. Bad news is, of course, that the run costs are very high. For every kilowatt of electricity you are buying, you're getting very, very close to 1 kilowatt. You certainly won't be able to get any more than 1 kilowatt delivered into the property as heat. And I would characterise the carbon reduction there as good. You know, it is better to do direct electric now with the carbon content of grid electricity than it is to burn gas. Let's compare that now with air source. So there is a significantly higher installation cost. but the run cost is significantly lower. Remember that COP of 2.2, it's going to be less than half, of the run cost of direct electric. And because we are using less electricity by a factor of 2.2, it is a much better reduction in carbon. Boreholes for ground source, particularly at individual domestic scale, are expensive. As you get bigger into multiple residentials, then the economies of scale are important and will really reduce those install costs. But the borehole costs of the system are higher. The run cost, however, is very low and is the best carbon reduction compared to the other technologies above. Horizontal systems come in cheaper, less expensive than borehole systems, will have the same run costs. The parameters that are used to design boreholes and horizontal systems mean that the run costs are going to be very, very similar, and again, they'll consequently deliver the best carbon reduction available. Water wells vary tremendously. It depends on where you are in the country. It depends on whether there's an aquifer there at all. It might not be even feasible to do a water well. So water well cost varies tremendously. It can be a very economic installation in certain parts of the country where water is readily available close to the surface. It can be very expensive, in fact prohibitively expensive. And again, run costs will be as good as the others, or sometimes even better, and the run cost, the carbon cost, is going to be the best available. Pond and lake systems come in very economic. Actually, they can come in on cost parity with an air source installation, deliver the same run cost savings again and carbon savings as the others. And I'll just mention mines for the sake of completeness. I've said price on application. To interface with an existing mine could be a hugely expensive operation. It could be inexpensive. I've dealt with one client up in Scotland who's got mine water coming out of the ground on its own, and they use that as a source for their large house system. Again, run costs and carbon reductions, very similar. So that's it for today. Next time we're going to talk about the problems we might encounter in heat pump systems, and importantly, the solutions we can help you with.